we went through quite a lot of stuff, right? We went through a bunch of covariance algebra steps, how to get to this point, and how to figure out how to find the covariances and variances of all these items in this. I mean, you gotta think this is just a 3 variable, small, simple regression, path analysis. You can see how much more complicated this will get as the models get more complicated. We walked through sort of how to develop like all these covariance algebra equations that will give us all the components we need. And then in the background, I ran the model through Levon, and we got to this point where we have, here's all of the coefficients and stuff that would be estimated based on this model. So we can then go through and like reproduce the matrix. We figured out exactly what these numbers are supposed to be. So for instance, the first one, it says that the covariance between x1 and y we had figured out was gamma 1, 1 times the variance of x1, right? So this is gamma 1, 1 times the variance of x1. So that's that 0.396 and times 0.951. So we can start figuring that out. And if you have a calculator handy, you can help me figure it out faster. So yeah, 396 times 0.951, 0.377. Next one's a bit longer. I don't know if I have enough room to do it, but let's see. So beta 21 is 0.286 times, now we could either put these numbers back in again, 0.396 times 0.951, but we just figured out that that was 0.377, and that's what's in these parentheses here, so I can just put that in there, times 0.377 plus, gamma 21 is 0.525 times 0.951 again, Alright, so these are together, those are together, and again, 0.607. All right. Now for an even longer one. If you actually look at this carefully, there really is right here. This is already 0.377 again. Right? We technically have that again here with this and this together too, right? So that pops up quite a bit. So some of this can be simplified down a little bit to, this is going to be, the gamma 1, 1 again is 0.396 times the beta 2, 1, which is 0.286. Again, we can swap this part out that's in parentheses with, again, 0.377, so we already figured that out before. And I'm going to add to that. I also have, again, a gamma 2, 1. If I actually look at this, times a gamma 1, 1 times that. So those together also make 0.377. So gamma 2, 1 is 0.525 times 0.377 again. If I'm doing that correctly, that should make sense. Plus an additional beta 2, 1, which is 0.286 times the error variance of E1, which is 0.511. What's all that? .387. Okay. This one is just given to us. It's like the easiest one of all of them, 0.951. Okay. So here we got, now these are squared. This is gamma 1, 1 squared times the variance of x1 plus the variance of e2. Okay, so gamma 1, 1 is 0.396 squared times the variance of x1, which is 0.951, plus those two, 0.511, which is the variance of E1. What's that? And then lastly, crazy long one. I'll do on the bottom here. Let's go. Yeah, let's do this. Down here so I can get down. So beta 21 is 0.286. Right, so 0.286 squared. Now in here, there's that 0.377 again, right there. But this is 0.37. Actually, it's not. I lied. It's squared. So never mind. I got a little ahead of myself. So brackets. Gamma 11. Sorry, gamma 11 squared is 0.396 squared times the 0.951 again, plus the variance of E1, 0.511, 2 times beta 21, which is, I already said it, 0.286, times gamma 21, which is 0.525. Right? Now, that is times, that thing together is 0.377, so we can stick it in there. All right, so that's all that. Plus gamma 21 squared. Gamma 21 squared is 0.525 squared times the variance of x1, 0.951, and then plus the variance of e2, which is 0.499 equals to what? That sounds correct. Okay. So we're able to reproduce all the parts, 0.377, 0.607, 0.387, 0.660, and then 0.928, or all 6 of those components have been reproduced. Now, it should be reproduced perfectly. I mean, it should be exactly the same, but I'll show you in the next slide, which I'll give you a second if you're writing this down or still trying to go through this, but all this is reproduced in the next slide. But just in case you want to write down this stuff, I'll give you a second. Everything we did is reproduced here, just in case my handwriting is too messy to go through, but everything's going to multiply through, right, to 0.377. We got 0.607 before, we got 0.387. The variance here is just sort of calculated. We don't have to estimate really anything. 0.660 for the covariance of, or the variance of y1. And then the last sort of crazy one, 0.928. Okay. The whole point of this that we spent, this is what, like the 4th day on, right? So we spent 4 days talking about this. This is an important aspect of trying to understand what it is you're doing. So when you're trying to set up a model, right, the whole point that Q equation we talked about is, as the program is trying to come up with estimates, to kind of come up with coefficients for your model that are the best for that model, it's doing so to try to make this process that we're doing is trying to pick coefficients to make your estimates as close as possible to the original data matrix. Right? So that's what's going on behind the scenes. Even though we're not really going to talk about how exactly it does that or how it picks those coefficients, I want you to understand sort of what is driving the estimation process. We're trying to make that Q value, the square difference between the S and sigma data matrices, we're trying to make that as small as possible. It does that by picking those coefficients that make that difference as small as possible. Sometimes, like in this case, because we're able to estimate everything, right? We come up with 6 coefficients for 6 data points, so we should be able to recover it perfectly, and the difference should be 0. That's not always going to be the case. We're usually trying to reduce. We're trying to get less. We're trying to get smaller numbers of estimates compared to the number of data points. So there's going to be times when the estimates are not going to be perfect. You're going to get estimates that are different. This is like the nice, easy, perfect case where we are estimating, we have 6 coefficients that we're estimating, and we have 6 data points. So it's a saturated or just identified model. So what that should do is when we get to here and look at, here's the original covariance matrix, right? This is just computing the covariances and variances for the data points. And really the data points are the 3 variances and then 1 set of covariances, because we don't count them twice, right? They're just repeated. What you notice is a couple of things. Everything comes up pretty well, except for this one, right? And this one, they're a little bit off. And that's not an issue with the estimation procedure. At least I don't think so. It's just rounding. We did everything to 3 decimals and sort of rounding. So our estimates, it's one of those weird things. If you carry 3 decimals as you're computing things, right? Your estimates, you get out of your products here are only really trustworthy to the 2nd decimal, not really to the 1st, right? Because we carried 3 the whole time. So the 3rd decimal oftentimes gets a little bit funky when you're carrying that way. So here we got 0.662, then we got 0.660. Here we got 0.930, but we estimated 0.928. So if we had carried more, how many more, I don't know, 5. I have a feeling a lot of these programs carry like 5 or 6 decimal places behind the scenes. So we would have got a little more accuracy in terms of that 3rd decimal, but these are still close enough for what we're trying to do here. These are pretty much the same. All right, so the whole point is we're trying to find the sigma theta matrix based on that model. And to do that, we specify a model, make sure that's identified. The program then comes up with those coefficients, the sort of in the black box, right? The 0.936 to 525, the 0.286, as well as the 0.511 and 0.499. Those are all things that are getting estimated as part of the model. And after they get estimated, they get converted back to this sigma theta matrix. And we compare it to original. And the idea is, if our sigma theta matrix, our matrix that's based on the model that we specified, if it comes really close to our sample covariance matrix, then that's evidence. It's not proof, but it's evidence that it likely is what's going on in the population, that our model actually is describing something going on in our population that explains why we're getting these variances and covariances in our sample. And so it seems a bit backwards, right? We're specifying a sigma theta matrix, right? Sigma theta matrix that is the population. We think this is what's going on in the population, and we think that by specifying that, it's going to explain what's going on in S. S we have. S we just, we compute it. We figure out a model to try to explain what's going on in S. So we're thinking this is why it's actually called sigma theta. Actually, I think oftentimes when you see it, it's written out as let's see, the sigma theta this way. I think that's confusing because it looks like some theta, but anyway, so the sigma theta matrix is what we're specifying, and we're trying to estimate coefficients for that model to get us as close to explaining this as possible. And that's where model fit comes in. The better job we do explaining S, the better fit we have, right? The more fitting our model is at explaining that S matrix. Right? We have poor fit. It means something we specified here is missing some components that isn't being captured in S. Right, so we're going to talk about that more in just a second. A different way of sort of looking at this is that somebody somewhere figured out that if you actually look at all that covariance algebra and look at all those crazy equations we went through trying to solve for the covariances and variances, someone figured out, all right, if we just look at the models, we can actually figure out what's going on. Like we can actually what's called a path tracing rules. We can just trace paths in the model to figure those things out without having to do all that covariance algebra. Right? So it's based on covariance algebra. It's sort of supposed to simplify things down. The problem is it's sometimes a little bit hard to apply these, and you'll see sort of why in a second, because it can get kind of confusing. So once parameters are estimated, you can calculate the implied covariance matrix. So this is oftentimes the implied covariance matrix. It's another word for sigma theta. It's the matrix implied by your model. Right? So rules for implied variance. So for common variance, what does that mean? So remember I talked about this before, that for every endogenous variable, their variance is split into two parts, right? The variance for any endogenous variable is whatever variance is dependent on the predictor is the common variance. Now that's confusing a little bit because we usually talk about common variance with factor analysis, right? The factor analysis, we talk about common variance of stuff shared, right? Well, in regression terms, the slopes, represent the part of the variance of a predictor and outcome that is shared, is common between them. And then the errors are the sort of independent or unique variances. So the same kinds of terms get used. We just have never used them in terms of regression, but the common versus unique stuff is still applies. So when we're looking at the common variance, trace a path from a variable back to itself, multiplying parameters. And then add to that unique variance of that dv, and that will give you the total variance for that endogenous variable. So think about it. Take the common variance, add in the unique variance together, should give you the total variance of the item. Rules for covariance between variables: trace path from one variable to another, and just multiply parameters as you go. All right, sounds easy enough. The correlation of covariance of any two variables is in a path diagram can be expressed as the sum of coefficients that connect the variables. So in tracing from one variable to another, you cannot pass the same variable twice, and no loops are allowed. I'll talk about that in a second. No going forward then going backward. Once you have traveled along a path forward, you cannot travel backward across that path. However, going backward and then forward is possible. What? So you can go forward, but then you can't go back. But if you go backwards, you can still go forward. As I say, the rules get a little convoluted, but only one curved arrow is allowed in tracing from the first variable to the last variable. What the hell does that mean? So when you're talking about an actual covariance in a model, which we don't have in ours, you can include that once, but you don't include it multiple times. All right. So one of the things, the reason I think the first time I taught this class, maybe I just went to the path tracing rules and quickly realized that it was probably a little bit difficult to do without talking about the covariance algebra. So I started talking about that too, because it can be kind of confusing. But let's walk through what it looks like, talk about some of these path tracing rules. For covariances, same rules, but you need to multiply the variances and covariances along the way. So you're looking at the covariances between things, you actually need to multiply not just the path coefficients, but also the variances and stuff as you go. When the beta paths, dv to dv, any gamma paths earlier in the model need to be temporarily replaced by a simple covariance. If I'm trying to connect a dv to a dv, the dv predicting another dv, right, the one that sort of has an arrow going out of it, when you're actually tracing backwards, you're going to use the entire variance of that variable instead of just the error variance or something like that. So we'll talk about that in a second too. The variances start with a variable of interest, trace back to any variables predicting it, and then back to it again, multiplying along the way. Add separate paths leading back to the variable. All right, sounds like a lot of rules. Sounds like it's probably more convoluted than the covariance algebra, but you'll see it's actually not too bad. So when we're trying to reproduce the matrix, all right, 0.951 is the only one that is just calculated. Right? We don't have to worry about that one. So for the covariance between x and y, okay, so with y1, so we're going to start at y1. If you're trying to get y1 with x1, because x1 is the independent variable and y1 is the dependent variable, you start with y1 and then trace backwards. That goes that way. Okay, so you multiply along the way. So 0.396 times then the variance of the predictor, which is 0.951. So we get to 0.396 times 0.951. Right, so basically you're asking what connects y1 with x1. We get one path, so we're going to take y1, we're going to trace backwards, and multiply the path along the way, 0.396. And since this is the independent variable, we're going to multiply it by its variance, which is 0.951, giving us the covariance between x1 and y1, which is 0.377. Okay? That makes sense? So all we're doing is just tracing from y1 back to x1 and multiplying along the way. For the next one, which is for x1 and y2, right? There's two parts to that. So you have y2 here, right, relates directly to x1. And so there's this direct path. That's one way. So we can do that. We can multiply 0.525 times 0.951. We can just multiply that way. Right? But it also has the indirect effect where it connects to motivation and to back to x1 again, right? So there's this way too. So we need to include both of those. So we're going to start at y2. We're going to figure out all the ways we can trace backwards to x1. Start at y2. And we're going to trace backwards from y2 and then include the variance of x1. All right, so we're going to have a 0.525 times 0.95. 0.525 times 0.951. Right, so that's the parts there. Then we're going to go the other direction. We're going to go from y2 to y1 to x1. And we're just going to multiply the paths along the way. We don't include E1 in this. We're just looking at covariances. So this is the amount that y2 relates to y1, and then how much y1 relates to x1. And then we're going to multiply that by the variance of x1. So 0.286 times 0.936, or 0.396, I mean, times 0.951. We add those two parts together, and that gives us the covariance that is due to the direct effect of x1 on y2, and the indirect effect of x1 on y2 through y1. So this is the direct effect. This is the indirect effect. They're just being added together. And therefore we get the total covariance between x1 and y2. The parts are good. All we're doing is just tracing stuff and adding along the way, multiplying it along the way. Okay, let's go to y1 and y2. I'm sorry, that looks like apparently at first I said let's do the variance of y1. I don't know why it went strangely out of order. I think it's because of I'm going in terms of order of simplicity. It gets more complicated as we go. So if I want the variance of y1, the variance of y1 is sort of a strange, when you look at the variance, is you look at any variable preceding it and you multiply. So you start with the variable, like y1, and you go backwards, multiplying along the way, and then go forwards again. So you're going to start with any variable, and how can you get from that variable back to itself? Right? So how do I get from y back to y again? Well, I can't go forward, and you go backwards, right? Because I'm interested in stuff that's preceding it. Because remember, y1 is dependent on x1 because of this path. So I'm going to go from y1, trace backwards to here, and then trace forward again. So you're going to start with y1, and you're going to trace backwards from y1 to x1. So that gives you the first 0.396 here times the variance of x1, 0.951. And then we're going to go back to y1. If you think about that, it sounds kind of odd because it's like, well, we already did this 0.396 times 0.951 because that was the covariance between them. But if I want to know what portion of variance in y1 relates to x1, the portion, I need to take the path squared times the variance of this. That will give me the portion of variance, the actual proportion of it. So the fact we're going 0.396 times 0.396 here, that's that coefficient squared times the variance of x. So y, tracing backwards to x1, you get the variance of x1, and then you trace forward again. So it's 0.396 times 0.951 times 0.396 gives you the first part of that, because this is the common variance. This is the variance that y1 shares with x, the part in parentheses. Well, that's not going to give me the total variance of y1, right? That's the common variance with x1, but I also need to add to it the error variance down at the bottom. Right? So the error variance needs to get added in. When you add those two together, you get the total variance of y1. Common variance with x1 plus the unique variance gives you total variance. Okay, so far not too complicated. It's like it's some things to keep track of and stuff, but you can see it gets more complicated as we go, because when we actually go between y2 and y1, this covariance becomes complicated. Let's talk about that for a second. When we're looking at, you can see there's lots of parts. When we're looking at the covariance of y1 and y2, right? There's this large thing here. There's one big part. There's a couple parts in it. Got another part here too. So let's figure out how that works. So when trying to connect y1 with y2, I can, just like with x1 before, or just, before we were talking about how x1 and y2 relate, well, it relates directly, it relates indirectly. We get the same thing. Y2 and y1 relate directly, right, this way, but they also relate spuriously because x1 predicts both of them. So it's not the same thing as having direct and indirect effect. We actually have a direct effect and we have a spurious effect going that way. And that becomes a little bit tricky. It's not too bad. So we start off again with y2, because y2 is the thing that's most dependent, right? So if we're looking at y1 and y2, yes, they're both endogenous, but because y1 predicts y2, let's start with y2 and work backwards. One way I can start with y2. I can trace backwards, 0.286. Remember that rule, anytime you're tracing along a beta path, you have to include the variances of the predictors as well. So with betas, I'm going to take 0.286 times the entire variance of y1. So what was the variance of y1? We figured that out above. 0.396 times 0.951 times 0.396 plus 0.511. This whole thing is the variance of y1 that I've now included along this path. Because this is a beta, I'm going to take that path times this, okay? That's the sort of the rule for the betas. And so that's one part, this path times the entire variance of y1. So I did this twice. So I want to include the entire variance of y1. But the way that happens is I can either just take this times this variance that we already figured out, this part, right? Or I can just trace along the way. So this is a alternative way of thinking about this. Either just this times the variance of all this, or I can just continue to trace. I can go from here. I can then add in the 0.396. So 0.286 times 0.396 this way, right? Times 0.951, which is the variance of x1. So I've now come to a dead end. So I need to go back. How do I get back to y2? So I go y2 to y1, x1, and then go back, okay? So times 0.951, I'm going to hit another 0.396 along the way, back to here. And then because that includes the common variance of the x1, I need to add in the variance of e1 to make that the complete variance of y1. It's the only time when we have variances between, or covariances between endogenous variables using a beta like this, you don't include the variance, which means you're going to include the error variance at some point, which you don't do for other components, when you're connecting things through gammas. You can either think of this as just the entire variance of y1 that we had just figured out up here, that 0.660, right? Or you can trace all the paths back, which is still doing the same thing, because if I'm going from y1 to x1 back to y1 plus e1, that is the variance of y1 anyway. Okay. So how else are they connected? Well, I can go from y2 this way and connect them. So I can start, I just replaced that. So this whole thing, 0.396, 951, 0.396, replacing that with 0.660, all right? That's what we figured out in the line above. Let's replace that there. Makes it a little easier. So we can start with y1 and trace back to x1. And remember the rule about you can go backward and then forward, but you can't go forward and then backward, right? So if I go this way, I'm going backwards from y1 to, or y2 to x1, so 0.525 times the variance of here, right, the variance of x1. So I can do that, and then I can go forward to y1 and connect them. So backward, fine. Forward's fine. I just could not go backward again. Once you go forward, you don't go backward again. So going backward to x1 and then forward to y1 is another way of connecting y2 and y1, which is why you got the 0.525 times the variance of x1 times the 0.396. This part, 0.525, 0.951, 0.396. Multiply that together, multiply that out and add them together, you get the 0.387. Making the same thing. Questions about that one? So there are two parts, right? You get the part that looks at the direct connection between y1. So I went too far. Yeah, one part is direct connection between y1 and y2, which includes just including the whole variance of y1. Right? That's why we just replaced that part with this, right? 0.661. And then we have another part that is because of the spurious prediction of x1 to both y1 and y2, we can trace from y2 back to x1, forward to y2, and multiply along the way, which is that 0.525, 0.951, 0.396. So this part is due to the direct connection. This part is due to the spurious prediction of x1 to both variables. We add them together, and that gives us the total covariance between y1 and y2. So y2, the variance of y2 is tricky because there's many ways of getting from y2 back to itself. Right? I can go from here to there and back. I can go from here to there to there to there, and from here to there and back. Right? So there's lots of different ways of getting from y2 back to itself when trying to figure out the variance of y2, which makes this is why I save y2 to the end. It's the biggest pain in the butt. We can start by the simple path, simple way of going just from, all right, how do we get from y2 back to itself? I can go from y2 back to x1 back to itself. That's one way. So if I look, 0.525 times 0.951 times 0.525. 525 times 951 times 525. y2, going backwards, then multiply that with the variance of x1, and then go back forward again. Right, that's perfectly fine. That's one part. This is the part related to the direct path between x1 and y2. Okay. So we also have the direct path from y2 to y1. I can go y2 backwards to y1, but when I do that, I need to include the entire variance of y1, not just the path. That's why that 0.660 is in there again. All right, so let me go y2 back to y1 times the entire variance, right? Including the error variance and this whole thing together, which you figured out was at 0.661, or 0.660, I mean. And then we're going to go back to y2. Right? So here and back. That's the second way. So that's the first way, the direct prediction from x1. This is the direct prediction from y1. So there are two different ways that we can actually go from y2, sort of circa the whole route, right? We can go from y2 to x1 to y1 to y2. Or I can go the other way, y2 to y1 to x1 to y2. I can do those both ways, right? Which is why, just as a foreshadowing here, if I go back a second, the only place we see this 2 times beta 21 gamma 11 times the variance of x1 shows up under y2 is because you got those two routes. You can actually go one direction or you can go the other direction, and they're really the same coefficients being multiplied throughout. So instead of doing that with covariance algebra, we just say, look, it's 2 times all those things together. So here we can go from y2 to x1, right, including the whole variance of x1. Then we can multiply that through to y1, and then multiply it through to y2. So we can go that route. So we can go sort of counterclockwise around the loop. We can also go clockwise around the same loop, and are all the same coefficients being multiplied along the way. So that's why in the previous thing we actually got 2 of each, 2 of those things. The only remaining part is, so all that so far, this first part, the direct prediction from x1, this is the direct prediction from y1, this is the counterclockwise loop, this is the clockwise loop. So all 4 of those things together represent the common variance, the variance that y2 shares with all the other things in the model. Okay, so then we also need to add in the unique variance. The error variance here of 0.499 gets added in. We're looking at the variance of y2. You add all those things up. And here I got 0.929, and we got 0.928 before, but whatever, it's all the same. It's just rounding. I think the real number is 0.930 anyway. You see, there's all these different tracing things that someone, I think, thought would make things easier. In some ways, it actually makes it crazy, more convoluted. But if you actually practice it, get used to it, actually, it's not too hard to think about. You just got to think about, okay, with covariances, it's not too hard. You just sort of connect the variables together. With variances, how do I get from a variable back to itself? And if there are multiple ways, you just do it each of those ways and add them all up. And making sure with a variance, anything that's endogenous, you also have to add in the error variance to get the complete variance of that variable. Otherwise, you get the same results from both the covariance algebra and the path tracing rules, as long as you sort of apply them correctly, which can be sort of tricky. Again, the whole point of this is not to make you experts in covariance algebra or path tracing rules, that kind of stuff. It's just to give you an idea of the reason all this sort of stuff goes on in the background. So the big picture here is specify a model. There's some magic that happens behind the scenes in the computer program that spits out to us these coefficients. The motivation, what's motivating the program to pick those particular coefficients is to try to find coefficients that are going to make the model implied covariance matrix as close to the original sample covariance matrix as possible. And so it's picking those. The way in which it picks those depends on a couple things. Depends on the estimation method, like is it maximum likelihood or ordinary least squares, or those different things, like how it's trying to find those estimates is going to depend on the estimation method. That makes sense. It's trying to find those best estimates, and if it does a good job, or combined with the fact that you specify the model correctly, that your hypotheses are correct, your implied covariance matrix and your sample covariance matrix should be as close as possible, and we can actually look to see if they really are significantly different. We can do a test. That's what we're going to talk about next. We're going to leave all this crazy math stuff on. I'm sure most of you guys are going to be disappointed that we're leaving the crazy math things and going on to more theoretical, discussions of things. If we want, I'm happy to meet with you, like outside of class. We can do more math if you like, but if not, we'll just continue forward and talk about more theoretical things, like how do we actually do fit? What are these different fit indices? How do they work? There's a little bit of math in those because there's some equations there too, but nothing like the covariance algebra stuff. This stuff's a lot more straightforward. All right, so we'll leave the covariance algebra and path tracing rules and head back into the safer zone of theoretical things that we can talk a little bit more about and used as tools and not necessarily have to do a whole lot of math. Path analysis 3, which doesn't quite line up with the videos. I think we spent 3 days or something, or 4 days talking about the covariance algebra stuff. But this is basically sort of topic 3, which is looking at effects, model fit, and then talk about what's, to me, is probably the coolest part about this whole thing is this idea of a multi-group path analysis. That means how you can use it. All right, so this is a rehash. Some of the stuff's a rehash stuff we talked about before, but it's nice to just remind you that we have indirect and total effects. I should say indirect, direct, and total effects, but indirect effects are estimated statistically as the product of direct effects, either standardized or unstandardized, that comprise them. Remember, we talked about how in a Baron and Kenny type model, right, we estimate C, and X predicts Y, and then we have X predicts Y with these different paths in it. Call it Z, like that. And we called this Z prime, and we said that the product of the indirect effect is really just multiplying A times B. That's why it says the product of direct effects. So the way we actually can estimate the indirect effect of X on Y is by multiplying through. We just saw that with the covariance algebra. We saw that with the path tracing rules, that as you go to try and figure out the direct and indirect path, you just multiply the coefficients along the way of the indirect path to sort of figure out what that is. If you add those together, if you add A times B plus this C prime, it should equal C, where C is the total effect, C prime is the direct effect, and A times B is the indirect effect. It also means that C minus C prime equals A times B. I had the difference between the total and direct effect, that difference is the indirect effect. Okay. But they're also interpreted just as path coefficients. Total effects are the sum of all direct and indirect effects of one variable on another, right? So the total of the direct and indirect effects together give you the total effect C. So this, if you have no indirect path in there, right? Separate these out. If you have no indirect path in there, this is the total effect of x on y. We have not split everything up. It's just the total effect. It's not the direct effect, because in order to have a direct effect, you have to have an indirect one. Right? So you only talk about direct effects in relation to the indirect ones. If there are no indirect effects, this is the total effect of x on y. And we can split that effect up into the direct and indirect effects, which means if I add them together, I get the total effect. All right, well, that's good. We did a little bit of that in lab in trying to set up the mediation model, where we actually had to specify the A and B path and all that stuff. So if you look at the standardized indirect effect of fitness on illness through stress, fitness on illness through stress. Right? This is an example, I think, taken out of Klein's book. The standardized indirect effect of fitness on illness through stress is estimated here as, just take that path, negative 0.109 times 0.291, multiplying those paths together. And I get that that indirect effect is negative 0.032. You may be asking, why is this path dotted and that path solid? This is actually an assumption, because I don't remember. I'm pretty sure this path is not significant, and this path is. So they're showing that there's a non-significant path predicting fitness to stress here that they've left in the model for some reason, and you sort of multiply them through, you're getting the indirect effect. That's my guess. I'm pretty sure that's right. So that's just, this is just the indirect effect, which makes this 0.260 the direct effect, right? Between the two of them. Sometimes it's hard to see that. So we talk about, like, the picture I drew. Oftentimes in models, when we have direct and indirect effects, those aren't the only things in the model, right? We have all this other stuff going on. So how do we then, look at just the indirect and direct effects of these three variables, even though these other ones are actually in the model still? So we can still do that. We still can figure them out in the same way. It's just there's other stuff going on too. Right? There's all these other dotted paths here that I'm assuming are also not significant, because they're all small, close to zero. And the ones that are solid are the larger ones. So I'm assuming the dotted means not significant. Another way to think about that is the dotted ones or dashed ones are the ones that are more likely the paths you'd likely take out of the model. If I ran this model and I got that all these paths are not significant, I'd probably take them out. Right? It could also be the author's attempt at some kind of weird pentagram. Sort of pentagramish. Right? Maybe it's a Halloween thing. I don't know. But I have sometimes, done models, put the nodes at points just to make sort of cool designs in the path, but it doesn't always work out. This one definitely is. If you turn it sideways, it's definitely a pentagram in there. All right. If you actually then add up the 0.260 with that previous indirect path, that 0.292 is the direct path, is the total effect, on fitness on illness. And if you were to take this path out of the model, it's likely that this path would change to something very close to this 0.292. Because you take the indirect effect out, that previous direct effect now becomes a total effect. Some SEM programs optionally generate effect decomposition. They give you a summary of the direct, indirect, and total effects. Here's the bad news. Here, I'm draw a sad face. Okay, very sad face. Levon does not do that. Levon makes it a giant pain in the ass to get any of these things. Where most of the programs, it's literally like just a couple words, like in an EQS, effect equals yes, and then it'll just give you output for all the direct, indirect effects. For Levon, you have to specify exactly which indirect effects and direct effect stuff you want, and as part of the syntax, and it spits it out to you. So there's a trade-off there. Levon sort of makes it more complicated. It's also free. right? So there's the thing. Get a little more work, saves you some money. Right? EQS is not expensive, but it's not free. Right? Compared to something like M Plus that is a lot more, and you have to do like yearly renewals. There are programs, by the way, I should mention, like Amos, right? And I think Amos probably doesn't get enough attention when it should, especially here, because CSUN has a license for SPSS and Amos. So Amos is a structural equation modeling program that if you are able to download SPSS, usually you have the option to download Amos and also like Python and other stuff that comes as part of the SPSS package. So I don't really use Amos enough, and I probably should. There's certain things I have used it for, but I don't use it enough to really recommend it. Some programs also produce the total indirect effects when there are more than one mediating variable. Not a whole lot of them do this. I think Amos does, and I think M Plus does, but EQS does not, which is something that always drove me crazy about EQS. If you have multiple mediators, right? So I now have, let's say I have X and Y like this, and I have a Z. Right, so here's my previous mediation model. Great. What if I also have a W? So I have two mediation paths, two indirect paths. Some programs will tell you, let's say this is A and B, and this is, I don't know, D. I don't want to use C, that's confusing. This should be C. And this will make E and F for no reason. Okay, so most programs actually would just give you the total indirect effect. This means it's just going to compute how much X indirectly predicts Y by combining all this stuff together. It gives you just the indirect effect. It doesn't break down to you the indirect effect through Z and the indirect effect through W. So I'm talking here, some programs also produce a total indirect effects when there are more than one mediating variable. That's what EQS does. That's what I think M Plus does, is it just gives you the total. It'd be nice if they actually broke it down and separated it out, but the only way you could do that is to then rerun the model, taking one side out and taking the other side out to see what those indirect effects are separately. But it'll give you just the total indirect effect by multiplying and adding those two paths together. That's annoying, but it's what a lot of them do. However, standard errors estimates for unstandardized direct or total effects vary from program to program. So how exactly they compute the standard errors for this stuff, especially when there's more than one mediator, they do differ somewhat, but they're all going to be fairly close. Sometimes they use a Sobel method, sometimes they use other similar types of methods to estimate the standard errors appropriate for the indirect effects. I just realized I was standing here like with the sad face over my face. For example, some SEM computer programs report standard errors for total indirect effects only, but not for each constituent, each individual indirect effect. So what I was saying already. However, there's some hand calculable statistical tests for unstandardized indirect effects and recursive path models that involve only one mediator. So there's the places like, I forgot what it's called. There's a website that I think is, actually it's not even it. Chris Preacher has a website that helps with some of this stuff. There's a add-on module in an SPSS. It's called, I forget. It's called Influence. No, I forget. That actually helps to break down the different mediator effects and which ones are significant, which ones aren't. The best known for these tests is based on estimated standard error developed by Sobel. It's been around the longest. There's been papers written about how there are better tests. Sobel's still sort of stuck around. It's still been the one that's most widely estimated, most widely used. Hasn't changed much. And here's that Sobel method we talked about, I think at 524. All right, let's take the two paths, the two paths that go through the indirect effect. And to get the standard error, it's just that same path squared times the opposite standard error squared. All right, so A squared times the standard error of B squared plus B squared times the standard error of A squared. This gives you an overall variance for the path. Take the square root of that, change it back to a standard error, and then you can actually then test the A times B for significance. Okay. This is using the unstandardized coefficients, not the standardized ones. All right, so we talked about that before. It's not something new. Probably one of the biggest benefits or bonuses you get from doing an SEM model versus regression or some other using some other approach, is this being able to assess for model fit. Now that has changed some, in that in a lot of programs with even for regression and those kind of things, there are now methods to actually assess model fit for those as well. So SEM is not alone in it anymore, but for a long time that's sort of the way it was. But if you wanted model fit testing, you had to go through this sort of process. So after you specified your model and you figured out this identified and you're able to estimate everything, the population parameters are estimated with the goal of trying to minimize the difference. We just talked about that. We're trying to make them as small as possible. So we're specifying some sigma theta matrix, and the program is going to try to estimate coefficients for that model that make this difference as small as possible. Awesome. All right. We talked about this before, where W is a weight matrix depending on the estimation procedure. But again, the details are, here's our model specified matrix, and we want that to be as close to S as possible. Great. In fact analysis, we compared the covariance matrix, or the correlation matrix, and the reproduced covariance matrix to look at fit. Right? We want the residual matrix to be as small as possible, and we did that in EFA. But we didn't really have a test for it. We just sort of looked to see if there was any non-zeros, and that sort of gave us an idea of where things weren't fitting as well. And SEM, this is extended. So we actually take that Q value, the minimized value Q, we multiply that by n minus 1. This is our degrees of freedom based on the number of subjects we have. And if everything's specified correctly, we multiply this out, we get a chi-squared distributed value. So the difficult part of estimation is choosing the correct W matrix for the type of data and the model being specified. Oftentimes, computer programs are getting smart enough to know that for you. If you specify that your outcomes are dichotomous, for instance, oftentimes it will change from maximum likelihood to something else because it knows the maximum likelihood is not very good for that. So it sort of knows sometimes, oftentimes it doesn't, and you may need to figure out that you're specifying a model that doesn't really fit with that estimation procedure.